So second time, good morning. We will have today two lectures. The first will be about the degradation and synthesis of glucose molecule. And the second lecture will be about the degradation of fat. That means degradation of triacylglycerols and degradation of fatty acids. Yes? So you will see some similarities in both, in glucose and lipid metabolism. Before we will come to the glycolysis and gluconeogenesis pathway, we will start with some facts about the glucose. That means why it's so important for our body. What does it mean, the glycemia? That means the concentration of blood glucose. Then we will speak about the way how we can transport glucose through the membranes. For that's very important initial step when you want to start the metabolism of each nutrient. And then we will smoothly go to those two metabolic pathways. So if we start with the glucose. As you have heard from us many times, glucose has central position in the saccharide metabolism. What does it mean? That means that all saccharides that you have in the diet, or you can say majority of them, can be transformed to the glucose molecule. And on the other hand, if you want to synthesize some saccharide in your body, glucose can serve as the maternal precursor for it. Some examples, for example, if the mother wants to produce the mother milk, then inside the mammary gland you can transform glucose to galactose and then subsequently forming disaccharide lactose. The same thing if the cell wants to produce ribose, it will utilize some enzymes of the glucose metabolism, and there are ways how to transform glucose to ribose if the cell wants to synthesize new DNA. That means if the cell wants, for example, to replicate. There is very important energetic point of view for glucose molecules, and we can say that glucose is universal or general energy substrate for all our cells. Some of our cells are even strictly dependent on the glucose. That means that they use only glucose molecules, or they need very long adaptation to start utilizing other molecules. For example, erythrocytes, since they have no mitochondria, they can utilize only glucose for the energy use, since only glycolysis is able to give them enough ATP from the whole energy metabolism outside the mitochondria. And as you already heard around 2 weeks ago, our central nervous system, that means brain, is also utilizing preferentially glucose, and only after long-term starvation, after several weeks, it's able to use only 50% of glucose, and 50% of the energy demands are covered by ketone bodies. And one other important information is that glucose molecules are able to give you energy. Also, if you are missing oxygen, that means in the state of hypoxia, that's lack of oxygen and a lot of carbon dioxide, our cells can use glucose, the part of the glycolysis, without oxygen, and therefore they can gain some amount of energy from it. Example from real life, you have the skeletal muscles that must from zero activity switch to highly intensive activity. For example, if you decided you want to start running, and in that situation they must use the internal energy reserves and wait some time till the oxygen supply will increase. So there are some seconds when they are highly dependent on creatine, phosphate, on glucose molecules, on the glycogen. And that's due to the fact that glucose can give you, per one rotation of glycolysis, give you 2 ATP molecules. No other nutrient is able to give you this in so effective way. Glycemia is a term describing the concentration of concentration of glucose in blood plasma. When do you measure it? From your own experience. If you are sent to the doctor, yes, but now when during the day?
In the morning.
And why in the morning?
Because you are fasting.
Yes, for typically during the night we do not eat anything, and if the doctor tells to you that you should not eat your breakfast, then all of us are after some time of fasting. That means around 10 hours of fasting, and we can say that in that time the metabolism of all of us is in a very similar state. Yes, if you have no meal in the GI tract, you have no nutrients, and you can say that you have only your body internal stores to feed your glucose metabolism. Therefore, if you read somewhere the numbers, it should be the fasting level. Yes, if it's not fasting, that it's marked inside. Of course, that when the patient comes to the hospital, for example, at 2 p.m. due to some other illness, then you can measure higher values of the blood glucose level, and you will simply know that the patient is after lunch. Yes, and therefore it's normal to have higher, but it's not normal if it's fasting level. The normal fasting level should range between 3.3 till 5.6. And as you know, this number is very strictly regulated by two groups of hormones. The first group has one member, that's insulin, and insulin does everything to decrease the glycemia. On the other hand, we have the group of counter-regulatory hormones that acts against insulin, and therefore they are increasing glycemia. The two basic disturbances of glycemia are hypoglycemia, that means that you are below the normal level, and hyperglycemia, if you have values higher than the normal level. And as you know, hyperglycemia is typically based on the disease that's called diabetes. We have diabetes type 1, diabetes type 2, and that's basically the problem somewhere here. The problem with the production of insulin or with the effect of insulin in central tissues. And then you can have the secondary diabetes when you, for example, have the adenoma of the cells producing epinephrine. That means the cancer inside your suprarenal gland, inside the medulla. We call this adenoma pheochromocytoma, and it's producing the epinephrine, and therefore you have excess of molecules that are increasing the glycemia. And when this durates some time, you will develop hyperglycemia, and we call this secondary diabetes. Since the problem is not here, the problem is in the counter-regulatory part. As you know, diabetes is quite common. In Czech Republic, around 7–8% of population have diabetes, and the numbers are very similar around the whole Europe. So it's a very big civilization problem, and the treatment of patients with diabetes is very expensive. If you take it from the perspective that there are many complications and that it's typical chronic disease. So any questions to the basic overview? On this picture, you see the basic overview of the pathways that can give you glucose molecules or consume the glucose molecules. So here we have the glucose, and as you see, we have three main sources of glucose molecules. First source is glucose that's coming from your GI tract. That means glucose from the nutrient. Second source is the glucose coming from the glycogen. That means glycogen is the storage polysaccharide, and when you do its breakdown, you will release the glucose molecules, and this pathway we call glycogenolysis. The third pathway is called gluconeogenesis, and it's the production of glucose molecules from non-sugar compounds. Typically, it's pyruvate, some amino acids, or for example, glycerol. On this graph, you see how long these resources can feed you with the glucose molecule. So if you take that the time 0, it's your last meal, and since that you have no other meal, here you see how many grams per hour you should produce, or that means you will utilize. You can see when these three sources switches in their importance. So around first 4 hours after a standard meal, the main source of glucose is the diet. After that time, that means, for example, after or during the overnight fast, you see that you must have the glycogenolysis that's giving you the glucose molecules to your metabolism. And then you see that from around 16th hour, the main position takes the gluconeogenesis, and it can give the glucose molecules into the metabolism for quite a long time. Yes, it can be 5, 6, 7, 8 weeks. Yes, it depends on your body stores. It depends on your health state. But gluconeogenesis is the final and the ultimate pathway how you can produce the glucose. Glycogenolysis is the typical middle state, and the diet, as you see, is quite short term. Yes, after a typical meal. How do you utilize glucose molecules? First possibility is that from glucose you will produce new glycogen. That means the synthesis of glycogen. Or you can send glucose to the glycolysis. That's converting it into the pyruvate. And then from pyruvate, you typically go to the oxidative decarboxylation of pyruvate. That means production of acetyl coenzyme A. And here you can decide whether you will produce energy in Krebs cycle and respiratory chain, or whether you will transform acetyl-CoA molecules to fatty acids, and they will esterify glycerol, producing triacylglycerols. Therefore, if you have, for example, meal that's very rich in glucose, then the fate is quite simple. You will produce glycogen, and then you will run glycolysis. Some amount will give you energy, but very big part can be transformed to free fatty acids and to triacylglycerol. That means that from saccharides you are able to produce lipids, and this whole pathway is accelerated by insulin. Yes, for insulin is willing to decrease blood glucose level. As you know, we said to you that the central position inside the metabolism typically has the activated compounds. And therefore, better to say that the central is glucose is better to say that the central position has glucose 6-phosphate. Since glucose 6-phosphate is activated version of glucose, and it's the same as you have fatty acid and acyl coenzyme A. The activated part of the molecule is acetyl-CoA, and the active glucose is glucose 6-phosphate. Yes? Therefore, you can read both that glucose 6-phosphate has a central position in the metabolism, or glucose itself. If we now look how the glucose molecules are transported through the membrane, so could you repeat me how, in general point of view, we can transfer compounds through the cell membrane?
Facilitated diffusion.
Good, so we have facilitated diffusion. That's one possibility. How it's done? What's the principle of this transport?
Moving from a region of high concentration to a region of low concentration.
That's in general diffusion, that's true. And what does it mean, facilitated diffusion?
You know,
That's true, you do not need energy, and you have some channel, yes? So the best thing is that you say it's movement from high to low, that's true. It's moving without energy, since the energy is done by the movement itself, or it wants to move from high concentration to low. That means everywhere will be the same. And it must be done by some transporter through some channel. And the point of movement can be blocked if you close the channel. That means that very often you have some signal that opens the channels. What other types of transport do you know? So we have phosphorylated diffusion. Second possibility is? Good. Good. So I wanted to say passive diffusion, that means without channel. And now we have active transport, and we have basically two types of active transport.
Primary and secondary.
So primary active and secondary active. What's the difference behind this? Good. So the primary one is you have pump, and the pump directly utilizes ATP. That's the energy. Secondary, that will be, for example, for glucose, means you have two partners. One is moving along the concentration gradient, the second is moving against the concentration gradient. And the movement of the partner along the concentration gradient is giving energy for the movement of the other partner that's moving against the concentration gradient. And the last is typically the movement through the vesicles, but that we will not use today since it's typical for big molecules. If we look right now at the two basic types of glucose transporters, then we have these two basic groups. The first is SGLT1 and 2, that means sodium glucose transporter. We have two basic types, and it's the ideal example of secondary active transporter. That means that you have sodium plus glucose moving through the membrane, and sodium is here working as the horse that's draining the glucose inside the cell. That's due to the fact that outside the cell you have high sodium, inside the cell you have low sodium. But you need to keep this concentration gradient, and therefore you must have here some active pump that's pumping the sodium outside the cell, and that's the well-known sodium-potassium ATPase, NAK ATPase. And here you utilize ATP, and therefore we call this whole complex as the secondary active transport. And you move glucose and sodium, therefore sodium glucose transporter. Where inside our body we can find this transporter? Typically you found it at the places where you have something that we can call the internal surface of our body. And this transporter enables us to transfer the molecules from the internal cavities inside our body. Two basic examples. Our GI tract is a very, very long tube. And if you want to transfer, for example, glucose from it, you must have some active transport. You must give energy to it. Therefore, sodium glucose transporter type 1 is typically found inside the intestinal epithelial cells, that means in enterocytes. Second are tubular cells inside our kidneys, inside the proximal tubule. For at the very beginning of formation of urine, you produce around 180 liters of urine. And as the final, you know that you want to urinate around 1 to 2 liters of urine. That means that 178 liters of primary urine must be returned inside our body, and therefore also the glucose molecules must be returned inside our body. Therefore, the SGLT2 you typically find inside our proximal tubule cells inside kidneys. Second type of these transporters for glucose are called Gluts transporters. Here we have 1 to 7, but if you look right now in the books, you will read around 1 to 9, while 1 to 13. For us, this doesn't matter, since we want you to know especially these 4 transporters. The principle here is quite simple. You have channel, and the channel opens, allowing the glucose molecules to enter the cell or to move outside the cell. Since here it depends on the concentration gradient. If you have a lot of glucose inside, then the glucose molecules can go outside the cell, but of course predominant movement is inside the cell, for the cells are consuming the glucose. For example, erythrocytes or central nervous system. Here, as I told to you, is possibility that the channels are opened only when you have some signal. And therefore, we distinguish 2 basic groups of Gluts transporters. First are insulin sensitive, that's GLUT4, and the other are insulin insensitive. Or better to say, they are not regulated by insulin level. Why is this so important? As you know, we have several energy substrates in our body. And as you know, glucose is from some point of view limiting. Yes, for you have only limited amount of glucose in your body and only limited amount of molecules that can give you glucose. And therefore, some tissues can use glucose molecule only when there is really good amount of glucose, typically after a meal, when you have a lot of glucose and a lot of insulin. And if you are starving, when your glucose level is lower than after a meal, and your insulin glucagon ratio is also low, that means that you have not so many molecules of insulin in your body, then these tissues should use the alternative energy substrate and save the glucose molecules for other organs. Therefore, as you see here, the GLUT1, that's typically insulin insensitive, that means it's not regulated by insulin, is in those tissues that are strictly dependent on glucose. That means in central nervous system, that's covered by the blood-brain barrier. Yes, that's the barrier protecting the brain from the internal environment. Or you can find them in erythrocytes. Since both these types of cells must have the constant delivery of glucose, independent on the insulin level. Very similar, you have the GLUT2 transporters. As you see, GLUT2 transporters are coupled with the cells that have the SGLT1 and SGLT2. That means that in kidneys, in enterocytes, you want to release the glucose that was absorbed by the SGLT1 or SGLT2 inside your body. And these GLUT2 transporters are located at the basolateral membrane of the cells. The SGLT1 and 2 are at the apical membrane, that's to the lumen of the GI tract or the tubules in kidneys, and then at the basolateral membrane you have GLUT2. Also GLUT2 you have in liver and in pancreatic beta cells. That means in those 2 types of cells that are strictly regulating the glycemia. Pancreatic beta cells are producing insulin, and therefore it's logic that the transporter for glucose are not dependent on insulin.
Which ones are on the apical surface?
This and this typically you can say. Sorry, if you mean in apical surface, you have this type of transporter, and this is at the basolateral. Yes? Since the first you must absorb, if you have the glucose from pasta in your GI tract, you must absorb it into the cell, and then you must release it into the bloodstream. So first is SGLT, and then you have GLUT2. So pancreatic beta cells are producing insulin, and therefore it's logic that, that their transporters are not dependent on insulin. And the similar thing is for the liver, the main executive organ regulating the glycemia. And the GLUT4 That means the transporters that are located inside the cell membrane in high densities when there is some insulin inside the blood these transporters are in adipose tissue, in skeletal muscle, and in heart muscle. And therefore, we also sometimes these cells called insulin-sensitive tissues. It's not fully true, since insulin receptor you have almost everywhere. Yes, you have them in the liver, in your kidneys, almost everywhere. But only in these three types of cells you have the GLUT4 transporter, and therefore the insulin is also regulating the entry of the glucose inside these cells. That means that the importance here is slightly higher. And these cells can, in high quantities, use the glucose only if you have the insulin. That means only after a meal. That means if you have 2 days of starving, low insulin, that means lack of these molecules inside the membrane, and the glucose is preserved for these tissues, but not for the adipose, skeletal, and heart, since they should utilize fatty acids and ketone bodies. And therefore, more glucose molecules you have for your brain, erythrocytes, etc. So do you understand this?
Yes.
Good. Phosphorylation and dephosphorylation of glucose. How do we call enzymes that phosphorylate compounds? Kinase. And a group and enzymes that dephosphorylate molecules? Very good. And what does phosphorylases? There's a third group of enzymes handling with phosphate. For example, we will meet glycogen phosphorylase.
Adds a free phosphate.
So they do the phosphorylated cleavage. That means they use inorganic phosphate to break some bond. Yes? So these are three enzymes that work with the phosphate. Kinase and phosphatase, and then phosphorylases. Yes? Typical example of the third is glycogen phosphorylase. But today, we will stay only with kinase and phosphatase. The first, if you want to phosphorylate glucose, the whole story here is quite simple. You have neutral glucose, you want to produce glucose 6-phosphate, therefore you need to have enzyme called kinase, and you need to have ATP. When you produce glucose 6-phosphate, this glucose is activated, and it's the breaking point to several pathways, the glucose 6-phosphate, to glycolysis, to pentose phosphate pathway, or to synthesis of glycogen. What makes the phosphorylation slightly more complicated is that we have two enzymes catalyzing the same reactions, and as you know, these enzymes we call isoenzymes. That means enzymes that catalyzing the same reaction, but they have different structure, they can have different regulation, and they can have different physical and chemical properties. The enzymes are called Glucokinase and Hexokinase, and I will right now try to tell you what are the differences between these two molecules, and why it's useful for us to have two enzymes catalyzing the same phosphorylation. The glucokinase is typically located inside hepatocytes and pancreatic beta cells. And as you know, these two cells have, or group of cells, have quite unique position inside the glucose metabolism. Pancreatic beta cells are producing insulin, and hepatocytes are, in the response to the insulin or other signals, are regulating the blood glucose level. The glucokinase work, in some point of view, as a sensor for the glucose inside the pancreatic beta cells. And it could be quite understandable from this picture, since this is the curve of, here we have the velocity, here we have blood glucose concentration for the glucokinase. And what should do the pancreatic beta cells is according to the actual level of glucose to regulate the production of insulin. If the blood glucose level is high, more insulin molecules should be released into the bloodstream, decreasing the blood glucose level. If there is lack of glucose, then the pancreatic beta cells should stop the production and secretion of insulin, resulting in keeping the blood glucose level at a stable value. And as you see here, the Michaelis-Menten constant for the glucokinase is around 10. That means that, as you know, the physiological concentration in fasting is around 3.3 to 5.6. So if we say that it's around here, you see that in physiological concentration, the reaction, the velocity of the reaction is quite slow. And after a meal, when you shift here, you see that there is quite big increase of the enzymatic catalyzed reaction. That means that the glucokinase and the subsequent metabolism of glucose in the pancreatic beta cells is producing ATP in that cell, and the ATP production is modulating the velocity of the release of the insulin inside the bloodstream. In detail, you will review this process in the summer semester, but from this you should take that glucokinase is regulating the insulin secretion, or it's one of the key breaking points where you will decide how big the secretion will be. And that's due to the fact that it's able to regulate its activity according to the blood glucose level. In fasting state, very slow velocity. After a meal, very quick velocity, or much quicker. And why in the liver? What I told to you are the values in the peripheral venous blood. For typically when you go to the doctor, he collects your blood from the venous, from the veins. But after a meal, inside the liver, or inside the blood coming to the liver, is the blood glucose concentration much, much higher. All blood that's coming from your GI tract, from unpaired organs in abdominal cavity, is drained through vena porta, and vena porta is coming inside the liver. That means that if you have saccharide-rich food, the glycemia in vena porta can be very, very high. It's not 3, it's not 5, it can be 20. And in that state, the key role of liver is to reduce this high level, to consume the glucose, and to let inside your body to go only some amount of glucose molecules. And therefore, if you look that the liver hepatocytes can meet concentration around 20, you see how big difference is when you are after a meal, that means 20, and in fasting you have 3, 4, 5. And this big rise of velocity for glucokinase is a very effective way how the hepatocytes can consume the excess of glucose molecules from the diet and keep the shifts of the glycemia at some normal value. That means after a meal you will rise of glycemia, but you should not have, for example, 15. That means that you have diabetes. You should be at some level around 7, 7.5, or 7.7. That depends on the recommendations. Do you understand this, why glucokinase is good in these two cells? Hexokinase, as you see, has absolutely different shape of the curve. The Michaelis-Menten constant is 0.1, and that means that it doesn't matter if you have concentration 5, 10, 3, since it has almost the maximal velocity. And the way of regulation of this hexokinase is quite simple. It's inhibited by its product. That means by the glucose 6-phosphate. And the meaning of this is quite simple. Hexokinase phosphorylates the glucose molecules that enter the cell unless there is accumulation of the product. That means when the cell is utilizing the glucose 6-phosphate, hexokinase will produce new glucose 6-phosphate molecule. If you have some blockade, if you inhibit the utilization of glucose 6-phosphate, there is no meaning for producing of new glucose 6-phosphate molecules. So this is example of very short feedback inhibition, accumulation of products, inhibits the whole enzyme, and you will save glucose molecules, and therefore there is no concentration gradient for Gluts transporters, and no new glucose molecules are entering the cells. So for erythrocytes, they are utilizing the glucose, but of course only at some velocity, and it's wasting of your time to make it double, triple the velocity, yes, since there is only some level of metabolism inside erythrocytes. So do you understand this, the hexo and glucokinase? It's typical question for the test or for the exam. Yes, what's the differences between these two enzymes? For it nicely shows why in different tissues you should have different enzyme. And the opposite reaction is much more simple. You take glucose 6-phosphate, you cleave off phosphate, and you have glucose. Enzyme has simple name, substrate and phosphatase. That means glucose 6-phosphatase. And the only thing what makes it difficult is that this enzyme is not located in all tissues. This enzyme has specific subcellular localization and organ location. The organ location is inside the enterocytes, inside the proximal tubules of kidneys, and inside the liver. Why you have it in enterocytes and in proximal tubules of liver is quite simple. You take the glucose through SGLT1 or 2, you phosphorylate the glucose, and when you want to release it into the bloodstream, you must remove the phosphate. So it's quite logic that without this enzyme inside your blood would be the glucose 6-phosphate, and that you do not want to be true. And the same is in liver. Since liver is the main organ for gluconeogenesis, it must have effective way how to produce free glucose molecules. That means that liver cells are able to produce glucose 6-phosphate, and in the last step they must remove the phosphate, releasing into the bloodstream the free glucose. And as you see, kidneys and enterocytes are also able to produce free glucose molecules, and therefore all these three organs are the big three organs that are doing gluconeogenesis. That means during starvation, the gluconeogenesis is located in liver, kidneys, and enterocytes, since they have the final enzyme that's able to cleave off phosphate from glucose 6-phosphate. Second important note is where this enzyme is located inside the cell. The problem is that inside the cytosol you have the hexo or glucokinase. And when you want to produce free glucose in cytosol, it's quite nice, but the glucose and hexokinase could do the new phosphorylation of it. And this you want to prevent. As you know from a seminar, one way how the cells can regulate their metabolism is when they have two pathways that are one in direction, for example, glycolysis, and the other is in opposite direction, then some enzymes can be in the same compartment, but the unique enzymes are typically located in different compartments. And therefore, glucose 6-phosphatase is in different compartment than in cytosol, where you have hexo and glucokinase, and it's typically in the smooth endoplasmic reticulum. And this compartmentalization is important since you want to prevent the rephosphorylation by hexo or glucokinase. It's similar as synthesis of fatty acids you have in cytosol and beta oxidation you have in mitochondria. Two processes that are opposite one to each other and they are in different compartments. Any question to this? So if you have no question, then we will take the break till 55. And there you have. So can we continue? So in the second part, we will go first through the glycolysis, and then to the next lecture, we will take the gluconeogenesis pathway. Yes, that's the typical thing how we organize it. So glycolysis, as you already know, it's the part of the metabolism where you convert glucose to pyruvate or to lactate. The two different ends we will explain later. This pathway is in whole located inside our cytosol, inside the cytoplasm. That means that all cells have cytosol, therefore all cells can do it. And as you heard many times, it's the ultimate way how to produce energy, since it can be done everywhere. Only the problem is that it's not so effective. Yes, if you compare it with, for example, oxidative phosphorylation inside your mitochondria, the amount of energy produced here is quite small. Second importance is that through this pathway, you can convert saccharides to some simpler compounds, that means pyruvate, and then these compounds can be transformed to other nutrients. That means that you can look at the glycolysis as the producer of acetyl coenzyme A that can be subsequently utilized for the synthesis of fatty acids. On this picture, you can see three basic phases of the glycolysis. The first phase is the phase where you stay at the level of 6 carbon atom sugars. That means you start with glucose, and the last you have fructose 1,6-bisphosphate. In the second phase, you do the cleavage of 6 carbon sugar, that means fructose 1,6-bisphosphate, and you are producing 2 molecules of trioses. One will be aldose, the second will be ketose. That means that you will produce glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. And in the second phase, you have also interconversion of these 2 trioses. And the typical result is that you produce 2 molecules of glyceraldehyde 3-phosphate. Since this is the molecule that has the next enzyme inside the glycolysis. And in the third phase, you do the production of energy. Since here and here, you consumed 2 molecules of ATP, and therefore in the third phase, you want to generate some ATP. That means that you will modify the molecules of glyceraldehyde 3-phosphate to the molecule of pyruvate, and in these reactions you will generate some energy. And per 1 molecule of glucose you will generate 2 molecules of ATP in the whole glycolysis. If we right now look at the whole scheme of the glycolysis, you should, before I start with it, you should know all these reactions and all the intermediates. Glycolysis is a typical example, the same as the Krebs cycle, that you meet with high probability in the questions in the test, and it's the basic pathway where you should know the molecules, their formulas, and the main regulatory enzymes. Yes? That means we will here mention some enzymes that are highly important and that you should be able to write their name and to put it inside the right position in the metabolism. So if I start with the first reaction, that's the reaction that you already know. You start with glucose, you have glucose 6-phosphate, and the reaction is catalyzed by hexokinase or glucokinase. The subsequent reaction is the isomeration when you isomerase glucose 6-phosphate to fructose 6-phosphate. As you know, these molecules have the same number of carbon atoms. They are very similar. The only difference is that here you have aldehyde group and here you have the keto group. And if you have it in the cyclic form, you know that here you have -1 member of the cycle. In your books, you can see the formulas in this form, in the cyclic form, or in the linear form, yes? And it doesn't matter what form you will use for us, yes? Only you must be pretty sure that you know that here, as you see, is one more carbon and hydroxy group outside the cycle, yes? That's this carbon. As you see, the number of phosphates is still the same, and it's still on the 6 carbon. In the next reaction, catalyzed by the chief regulatory enzyme of the whole glycolysis, that means phosphofructokinase, you add a new phosphate to the first carbon. That means that you can say that here you have one hand with phosphate, here was one free hand, and therefore here you have now the hand occupied by phosphate. You utilize also ATP, therefore it's called kinase, and phosphofructo, since here we have phosphate and fructose. And this enzyme you must know, since it's the chief regulatory enzyme of the whole glycolysis. The product of this reaction is fructose 1,6-bisphosphate. And with this, we finished the first phase. So is this clear to you? In the second phase, you do the cleavage of the fructose 1,6-bisphosphate to 2-trioses. As you saw, here you have 6 carbons and 2 phosphates. Therefore, you will produce 2 trioses, and each of them has 1 phosphate. You know that you have 2 trioses. One is glyceraldehyde, the second is dehydroxyacetone. The difference is simple: aldose and ketose. And as you see here, each of them has 1 phosphate, so you have glyceraldehyde 3-phosphate and dehydroxyacetone phosphate. By simple isomeration, you can change dehydroxyacetone phosphate to glyceraldehyde 3-phosphate, and you do this since the next reaction is catalyzed with the glyceraldehyde 3-phosphate. But here you have possibility from dehydroxyacetone to produce glycerol. Yes, we will speak about this during the second lecture. And that means that sometimes you will catalyze the opposite reaction. That means that you can also go from glyceraldehyde 3-phosphate to dehydroxyacetone. But that's not the direction in glycolysis. In glycolysis, you convert dehydroxyacetone phosphate to glyceraldehyde 3-phosphate. This is the end of the second phase. So you started with 6 carbon atom sugar, and now you have 2 trioses. The next reaction is also catalyzed by the enzyme that you should know, and it's the only oxidative reaction in the whole glycolysis. When you do the oxidation, you know that the enzymes we call dehydrogenases. Therefore, this enzyme is dehydrogenase, and you take the name of the substrate. That means the name is glyceraldehyde phosphate dehydrogenase. Name of the substrate and type of the reaction that you do. Inside this reaction, you do several steps. Therefore, we will look at them more in detail. In glyceraldehyde, as you have in the name, aldehyde group is this. You can oxidize it to the next functional group, and that's the carboxy group. As you know, primary alcohols are oxidated to aldehydes, and aldehydes can be oxidated to carboxylic acids, to the carboxy groups. And that's the oxidation what you do inside. So the oxidation is the oxidation of aldehyde group to the carboxy group, and you can see the group here. That means here you have double bond oxygen, and here you have single bond oxygen. Why you do not see here this group is due to the fact that this reaction is so exergonic that the enzyme can take the inorganic phosphate and it's coupling this inorganic phosphate with the new formed carboxylic group. This is the new phosphate, this is the new carboxylic group, and when you take two acids together, you produce anhydride bond. So what you see here is the anhydride bond between the carboxylic acid and the phosphate. And as you know, anhydride bonds are very often macroergic. That means that in the subsequent step, we will produce the ATP. But if we stay here, the last question that we should answer is what's the coenzyme or cofactor used for the dehydrogenase. As you know, we have two basic options. We have FADH2 or FAD and NADH. And here you use NAD and you reduce it to NADH. That means that this cofactor is taking the electrons and protons from this aldehyde group, producing the carboxy group. Any question to this reaction? So you should know the enzyme, cofactors, and all partners coming inside this reaction. The subsequent steps are quite simple. Here we have anhydride bond, that's macroergic. So in the next step, you produce ATP. You simply destroy this anhydride bond, you release amount of energy that's necessary for the production of ATP. We call this substrate level phosphorylation. So production of ATP from some macroergic substrate without need to have an oxygen molecule. Therefore, yes? This is the only oxidation. Yes, and as you see from glyceraldehyde, here you have glycerate. Yes, 1,3-bisphosphoglycerate. That means the salt derived from glyceric acid. So no more aldehyde. That's this. That's the oxidation. If you remove the phosphate from the first carbon, you do not have 1,3-bisphosphoglycerate, but you have only 3-phosphoglycerate. In the next step, you do the isomeration, where you simply change the position of the phosphate. You take it from the third carbon, and you move it to the second carbon. Therefore, no more 3-phosphoglycerate, but new molecule is 2-phosphoglycerate. This isomeration you do since you want to do the next step. The next step is the reaction when you remove the molecule of water. That means elimination of water. You take this hydroxy group plus this hydrogen, and the enzyme is called enolase, and as you see, you eliminate water. As you know, enols are types of molecules that have double bond, and to that double bond you have bound the hydroxy group. So this is the example how it can look like. So this is double bond and this is hydroxy group. And as you know, this is enol form, and then you can have the keto form. And the keto form means that you have there the keto group. Here, by the enolase, we produce the enol, and the enol is phosphoenol pyruvate. If we look here, you remove hydroxy group, hydrogen, and here you have the double bond. That means you produce a double bond, and here this oxygen is derived from the hydroxy group. As you saw, here is the hydroxy group, only it was utilized for the formation of ester group with the phosphate. This phosphoenol pyruvate is stable since here you have the phosphate. And therefore, there cannot be the conversion of the enol form to the keto form. And in the last step, what you do is that you remove this phosphate from the phosphoenol pyruvate, and spontaneously, the molecule of enol pyruvate will produce the pyruvate. That means the enol form of enol pyruvate will change to the keto form of pyruvate. And since this reaction will produce the energy, the modifications of the molecule, you can gain energy from it, and the energy is enough to form new ATP. So this is the second position of substrate level phosphorylation in the whole glycolysis. First was here, and the second was here. The principle how you generate the energy is different, but in both these reactions you have enough energy to produce ATP. So is this clear to you? Do you have any questions to it?
Yes. The reaction between glyceraldehyde 3-phosphate turns into 1,3-biphosphoglycerate. Where does the oxygen come from? Because
here you have aldehyde.
yeah.
And so if we take the glyceraldehyde, the upper part of the molecule, so this is the glyceraldehyde, yes? This is the aldehyde group. What you do is that you convert it to carboxy group. This is the carboxy group. And then you take this group and you let it react in the subsequent reaction with the inorganic phosphate. And therefore, you see there the ester bond. Sorry, not ester bond, but anhydride bond. Since you have one acid, inorganic acid, one organic acid joining together, and you have the anhydride bond. So that means that inside, you see that it's one step, but you can schematically draw it, that you have aldehyde group, produce carboxy group, and this carboxy group joins the phosphate inorganic, producing anhydride bond. So one oxidation, and then the binding of the phosphate. And that's done in one step in the glycolysis. And then in the subsequent step, you release the phosphate, and you produce ATP from it. Some other question? So, yes?
What's the total balance of ATP?
That we will come to it right now.
If a phosphate is added, isn't it supposed to be aldehyde kinase, dehydrogenase?
Not for its dehydrogenase, since here you do the oxidation.
Of course.
And then this other you do not call inside the name. Of course that this is not the official long-term name. If you want, you can look at epoxy was the long name. This is the name that's shorter. That's the trial name, simply, or systematic way in the name. Substrate, enzyme. But
the phosphate comes from the name of the molecule and not from the name of the enzyme? Like,
yes, glyceraldehyde phosphate means that you have here glyceraldehyde phosphate.
not because it's
I think so.
enzyme.
Yes, I think so.
Okay.
For the typical second way how to call enzyme is substrate. What do you do with it? You have pyruvate dehydrogenase. And inside pyruvate dehydrogenase, you also do many other steps. You do the decarboxylation, oxidation, and you call it only pyruvate dehydrogenase complex. The same here. To the total balance, or I can do it here. The total balance is quite simple. -2 plus 2. But what's important is that here you have +2 with the first trials, and then you take the second trials, and with this you will produce other +2. That means you have -2, +2, and +2, and therefore the total balance is +2. That means that you have 2 trioses, and therefore this second part you do 2 times. Therefore you generate 2 ATP per 1 glucose molecule. Question is, when you finish with pyruvate and when you finish with lactate? The situation is quite simple. It depends on the redox state of the cell. That means at the amount of oxygen that can be utilized for the reoxidation on NADH. What is the problem is that this NADH must be reoxidized somehow to return to the reaction. If you do not do the reoxidation of NADH, then simply you are missing the cofactor for this enzyme and the whole glycolysis is blocked. And you have 2 options. First, reoxidize this in the respiratory chain. There is only one problem, that this is in cytosol and respiratory chain is in mitochondria. Therefore, you have the shuttles that are transferring electrons from cytosol into the matrix. But you should already spoken about them, yes, in the previous lecture. What's the second option is that you take this NADH and you put it on the pyruvate. And if you take the pyruvate and you reduce it, then, as you know, you will produce the molecule of lactate. The difference is quite small. Here you have hydroxy group, and here you have the keto group. And inside this reaction, you can reoxidize NADH. So there's the second option, what the cell can do if there is little oxygen inside, or simply when it cannot utilize it, is that it will convert pyruvate to lactate. Therefore, it will reoxidize the NAD plus form, and it can do the new glycolysis. And this is the typical way of action, how our erythrocytes are finishing the glycolysis, since they are not able to use oxygen, and therefore they will produce lactate as the final product, not the pyruvate. So do you understand this? Why do we have the enzyme that's called lactate dehydrogenase? So if no question, then we will come to the last, and that's the regulation. As I told to you, we have one chief regulatory enzyme, and then here you have some other regulatory enzymes. But what you should know in detail is the regulation done by the phosphofructokinase. The phosphofructokinase is a typical allosteric enzyme that can senses many signals from the cell. If I start with the first, that's the ATP-AMP ratio. Glycolysis is pathway where you produce ATP. And therefore, you should do the glycolysis in the situation when you are missing ATP. If you have a lot of ATP, it's wasting of your time to produce new ATP. That means that the high ratio ATP to AMP will inhibit the whole glycolysis. Similar thing you met in the Krebs cycle, where you have the energy balance, energy regulation in some enzymes. Second is inhibition by acidic pH. Glycolysis, you start with glucose, that's a neutral molecule. Pyruvate or lactate, they are acids, salt of the acids. That means that you start with neutral molecule and you produce two acids. This can lead to the acidification of the cell pH, and if the pH is low enough, it can harm the cell. Therefore, this is the self-limiting regulation, and when the glycolysis is too fast, it must be stopped since you want to prevent the damage to the cell. And here, all other pathways that are producing acids can indirectly regulate the pace of glycolysis also. Third is the inhibition of by citrate. Why do you think that this is done so? Why citrate inhibits the glycolysis? Where do we produce it? That's true. And now, the more difficult part, why citrate inhibits glycolysis?
Because it's made from acetyl-CoA. And if there's too much acetyl-CoA, that means we don't need to do the glycolysis.
That's true, to some extent. So we can say that we have two different compartments, glycolysis, mitochondria. But typical pace of action is that you have glycolysis, pyruvate dehydrogenase reaction, Krebs cycle, respiratory chain, or production of fat. And when there is accumulation of citrate inside the mitochondria, is wasting of your energy to produce new precursors for citrate, new molecules of acetyl-CoA or new molecules of oxalacetate. And glycolysis will produce you precursors of acetyl-CoA, and therefore when the Krebs cycle is inhibited or when it reaches the maximum velocity, is wasting of your time to produce new citrate, to produce new acetyl-CoA, and therefore citrate is a messenger from the mitochondria to the cytosol when it says there is enough of citrate inside, so you do not have to produce new acetyl-CoA, new pyruvate. The last is intermediate that's called fructose 2,6-bisphosphate. It's similar to fructose 1,6-bisphosphate, but 1,6-bisphosphate is inside the glycolysis, and 2,6-bisphosphate is regulatory intermediate. It's produced by a shunt by one enzyme that has dual enzymatic activity. You have one enzyme that's producing fructose 2,6-bisphosphate, and also the same enzyme can do the degradation. And the activity of this enzyme is regulated by these counter-regulatory hormones and by the insulin. What does insulin is that insulin dephosphorylates the enzyme, leading to the production of fructose 2,6-bisphosphate. The dephosphorylation will activate the activity of the enzyme producing fructose 2,6-bisphosphate, and this intermediate is activator of glycolysis. Therefore, insulin indirectly, through production of fructose 2,6-bisphosphate, activate glycolysis. It's logic, since insulin wants to decrease glycemia, and glycolysis is pathway consuming glucose. Opposite hormones, counter-regulatory hormones, will phosphorylate the enzyme that should produce fructose 2,6-bisphosphate, and in that state, it will switch off the activity, the kinase activity to produce the fructose 2,6-bisphosphate, and on the other hand, it will show the ability to destroy the molecule. And therefore, indirectly, the counter-regulatory hormones, through reducing level of fructose 2,6-bisphosphate, will inhibit the whole glycolysis. So as you see, the hormones do it also, the regulation of the glycolysis, and they do it indirectly. Or what's the second option is that these hormones also modify the transcription of the enzymes for glycolysis. So they have both the direct and indirect mechanisms. And the indirect one is through this highly active intermediate that's very potent activator of the phosphofructokinase.
What is the intermediate name?
That's this, fructose to 6-bisphosphate.
Yeah, where in which reaction is it being made?
That's the shunt when you take the fructose 6-phosphate and you do the phosphorylation on the second, or you remove it. Yes, and it's done by one enzyme that has dual enzymatic activity. It's able to do both. And the phosphorylation or dephosphorylation is modifying its activity, what will be predominant, and suppress the opposite.
What is the meaning of shunt again?
The shunt is, in general, shunt is that you have pathway and you do this. That means you have some metabolic pathway with some members, and then the shunt means that you take some intermediate from the pathway, and it depends where you return to it. You can return here or you can return back here. That's the shunt. That means that you take intermediate from one pathway and then you return to it.
What is this? The shunt?
Shunt, yes. Shunt or bypass. You can have, we will have 3 bypasses in gluconeogenesis. That's the same as you have bypass in coronary arteries. If you have obstruction of coronary arteries, the cardiosurgeons take the vessel and make the bridge. So any question to this?
Could you just say the citrate inhibition with the Krebs cycle, you know? Like,
Yes, the fact is that you have 2 pathways, different compartments. Glucose is metabolized in cytosol by glycolysis, and acetyl-CoA is metabolized by Krebs cycle inside the mitochondria. But the connection is that pyruvate is transported to mitochondria and undergoes the pyruvate dehydrogenase reaction, forming acetyl-CoA. That means that there is direct link between glycolysis and Krebs cycle. When you are producing citrate and you are utilizing it, then the glucose could be utilized also. But if you, by some signal, block the Krebs cycle, or when the Krebs cycle reaches the maximal velocity, is wasting of your time, energy, and potential to produce new acetyl-CoA from the glucose. Is wasting of the time. So in that time, the citrate serves as the messenger. Inside mitochondria, there is a lot of citrate, do not produce more.
How does it send the signal?
Simply citrate is transported into the cytosol. It has their transporter through the citrate shuttle, and you have a lot of citrate inside, and that means glycolysis. You should not increase your velocity, no more, for we are at the limit. Yes, of course, here you have some possibilities. First is if you give some metabolic poison and that you will block the Krebs cycle, then simply you cannot utilize it. Or the Krebs cycle can be at the maximal velocity, and therefore you should not accelerate the metabolism no more. And both these situations are plausible.